Hello and welcome to the final episode of the season finale of the Spring 2021 New York City Category Theory Seminar. And Juan Orendain is talking about what is the length of a framed bicategory. And take it away. Go.
Thank you very much, Nasan, and thank you everyone for coming. I've been to the seminar a couple of times, and it's a great pleasure to hear the talks. And now it's a great honor and pleasure to give a talk myself. So I was an undergrad, and I did my PhD at the National University of Mexico. I used to be an algebraist with a strong interest in operator algebras. While I was doing my PhD, sadly, my advisor passed away in the middle of it. So you probably don't know him, but so I spent most of my PhD years at the University of Tokyo working with the operator algebras group there. There I got a strong interest in what is known as coordinate-free conformal nets and categorical structures organizing coordinate-free conformal nets. And then it sort of went down to, or up to, pure category theory. Now I'm a postdoc at the National University of Mexico. So the title of the talk is, or the original title.
Thank you. That was perfect. Thank you. Go on.
Yeah, thank you. Thank you, Nathan. Yeah, so the original title of the talk is How Long Does It Take to Frame a Bicategory? In the last talk by Professor Street, Nathan mentioned this paper by Shanuel, What is the Length of a Potato, with the idea that I was nodding to that paper. Sadly, I didn't know the paper. It was just a coincidence, but I read it, and it's a lovely paper. So I changed the title to What is the Length of a Frame Bicategory, or a potato, or in this case, a potato is a frame bicategory. So just a very quick introduction to this. So I might say a few words that some of you might or might not know, but just I'll try to explain very quickly how I got involved in this project. So as I said, I was interested in these things called coordinate-free conformal nets. These are part of a version or a leg of the so-called Stolz-Teichner program. This was developed by Bartels, Douglas, and Henriquez, and their ultimate goal was to define these things, coordinate-free conformal nets, and organize them into a symmetric monoidal tricategory. They realized that they were actually looking for not a symmetric monoidal tricategory, but what they called symmetric monoidal internal bicategory. And the way they would define this, coordinate-free conformal nets are sort of parameterized binomial algebras, whatever that means. And so the main result, one of the main results in defining this would be the definition of a double category of binomial algebras, which was something that was expected, but it was very difficult to define. They could define this double category of binomial algebras in a very specific case, in the case of semi-simple binomial algebras or factors or simple things, and what are usually referred to as finite index morphisms, so just in a special case. So I started thinking about this problem, and well, the analysis or the theory of binomial algebras would not give any ideas, or give me or anyone any ideas on how to extend this double category to its general form. The techniques are very undeveloped, and people in the operator algebras community are really not interested in this or in developing these techniques. So this is very far away, like in the future, for people in the community. So I started to think about this categorically or pictorially. And so I've been thinking about this for a couple of years now, and this is what I want to talk about. So just start with the definition of a double category. So Nassan mentioned I should define things very, very clearly from the start. So a double category, or a pseudo double category, is a category internal to categories. The concept was introduced by Erzman in '63. A double category is a pair of categories, C0 and C1, the category of objects and the category of morphisms of C, a source and horizontal source and target functors, L and R from morphisms to objects, or left and right frame functors from C1 to C0, a horizontal identity functor, which we write as U, from objects to morphisms and a horizontal composition functor from this fiber product here to C1. So a double category is just that, a category of objects, a category of morphisms, source and target functors, an identity functor, and a composition functor. We assume that this satisfies the usual conditions that source, target, identity, and composition functions satisfy in a category, but we don't assume that the composition, or as we call it, the horizontal composition, is strictly associated for unital. So we assume that this is associated when unital up to natural isomorphisms, which we call associators and unitors. And we assume that these satisfy what you would expect the Maclane equations. If you haven't seen this ever, and it seems like a strange definition, just think about categories where every set or a class is substituted with a category, and every structure, function, domain, codomain, identity, and composition are substituted with functors. Again, we don't assume composition to be strictly associative or unital, but just we assume the existence, we have to give those coherence isomorphisms, and we assume that they're compatible. Okay, so these are double categories. We can use this idea of thinking of sets as categories, or promoting sets to categories and functions to functors, or classes to categories and functions to functors, to define in the obvious way double functors or double pseudofunctors or double lax pseudofunctors and double natural transformations. These are not important. The important thing is that we organize double categories into a two category. So I thought I could assume what two categories are, but I'll say what this is in a minute. A useful way of thinking of double categories is in terms of diagrams, as always. So there's a very nice pictorial representation for them. So suppose C is a double category. We call the objects and the morphisms of the category of objects C0 of C, the objects and the vertical morphisms of C. We call the objects and the morphisms of the category of morphisms C1 of C, the horizontal morphisms and the squares of C, and we draw these like this. So objects we represent as vertices, vertical morphisms as vertical arrows read from top to bottom, horizontal morphisms as horizontal arrows read from left to right, and squares or morphisms in the category of morphisms as squares like this. So if this is a square, this is its left and right frame, or its horizontal source and target, and this is its horizontal, sorry, its vertical source and target in the category of morphism C1. And we have operations. So we call the composition of squares in the category of morphisms of our double category C the vertical composition. We also have horizontal composition. So we have a bunch of diagrams like this, and we have a vertical and horizontal composition. And we implement this with this pictorial calculus as concatenating vertically, this is the vertical composition, and concatenating horizontally, this is the horizontal composition. So it's easier to think of double categories as a bunch of diagrams that you can compose like this. Yep. Okay, so here I was trying to compare double categories and bicategories. So double categories are a model for categorical structures of second order, which are modeled on cubes, on squares, or cubical model, and are modeled under this idea of internalization. They're internal categories on categories. There's another model, more popular, which is bicategories. So a bicategory, I thought I would assume what this is, but I can say what this is. So a double category, so suppose C is a double category. So a square in C is globular if it is of this form. So it's a square where the vertical morphisms or the source and target are identities. So a bicategory is a collection of diagrams like this. So it's a double category where every square is globular. So usually I can't draw, sadly. I thought about, I was trying to, well, I was planning on doing this presentation on my iPad, but I ran out of battery, so I can't write. But usually we squeeze these identities into points, and we draw globular squares as globular diagrams. And so we can think of bicategories or two categories as a bunch of globular diagrams that we can compose horizontally and vertically. So this is the more popular and classic notion of a categorical structure of second order. So we have a way of associating to every double category a bicategory, which is considered its objects, horizontal morphisms, and globular squares. We call this bicategory the horizontal bicategory associated to the double category C. We can organize bicategories into a two category, which is a bicategory where the horizontal composition is strictly associative and strictly unital. So the function associating to every double category, its horizontal bicategory, its collection of all these globular diagrams extends to a two-functor H from double categories to bicategories. We can go the other way. This horizontalization functor admits right inverses. For example, the trivial, vertically trivial, or the trivial double category. So this might not make a lot of sense after my definition of bicategory, but suppose B is a bicategory, then we can consider B as a double category just by taking all the squares being globular. So there's an embedding, which you write as bold H, from bicategories to double categories. And this horizontalization two functor and this embedding from bicategories to double categories are related via this adjunction here. There is another right inverse for this horizontalization two functor, or there are many rather, but we can define another pretty quickly, which is quintets, and this is a very classic and very beautiful construction. Suppose B is a two category, so assume composition is strictly associative and strictly unital. We write QB for the double category whose squares are of this form here, where phi is a globular square in B, so a two cell in B, and where this is a two cell from this composition to this composition here. So we represent the squares here as quintets like this. So I think the order here is wrong, but the idea is that we can represent this by parametrizing through the two cell and the composition of the boundary of the square. So QB is called the Ehresmann double category of quintets associated to the two category B. QB satisfies this equation here. The horizontal bicategory of the quintets of a two category is B, is again B. And the double category QB is edge symmetric, so it's special in a way. So the vertical morphisms and the horizontal morphisms are the same. It does not always happen, obviously. And this has more structure. It admits what is usually referred to as a connection, which was defined in Brown and Mossa by Brown and Mossa in '99, but this is not important here. The function associating to every two category, its quintets double category extends to a functor from two categories to double categories, which is again right inverse to the horizontalization two functor. This is defined only for two categories. So if B is a proper bicategory, we don't assume that the horizontal composition is strictly associative. And QB is not a double category, is what is known as a Verdi double category, which I won't define. So the main difference between these two right inverses, the embedding of bicategories into double categories and quintets, is essentially the category of vertical morphisms, the composition of the boundary, which is the main difference is these vertical arrows. So we just take globular diagrams and we just put them together in a certain way, just with that data. And well, the essential difference between the two constructions, or one of the main differences, is that in the trivial embedding, you get identities in the vertical morphisms, and in the quintets, you get the horizontal arrows as vertical morphisms. So I want to stress that, vertical arrows are very important. There are other very important examples of double categories. Morphisms can be organized into a double category. There's a classically in strict homotopy theory, there's a homotopy double groupoid associated to any filtered topological space. Classically as well, there's a double category of adjoints where objects are categories. Vertical morphisms are functors, and horizontal morphisms are adjoint pairs. So if you have an adjoint pair, you can compose them. You can compose this with the vertical morphisms reading from left to right or from right to left. And in my opinion, one of the most beautiful results in mathematics in general is that the choice is irrelevant. Through the calculus of mates of Professor Street, the two double categories are the same or isomorphic. So this is a very important double category. There's also relations where objects are sets, vertical morphisms are functions, horizontal morphisms are relations. And if you have a frame, there's a unique square filling that frame if the square commutes. So if you have a relation here and here, and vertical functions, if everything's compatible, then there is a square. Composition is the usual composition of relations. There is in my opinion, or not in my opinion, I guess, I've seen well, I wouldn't call it a rebirth because I was not around to see it not being being born in the first time. But I guess there's a bit of a boom, or I've seen double categories in a lot of places in the applied category theory community. They're everywhere. An example of this is David Spivak's double category of polynomial comonoids, or small categories by the Amanush-Dalul theorem. So he does a lot of things with this, a lot of very great things with this double category. There's also John Baez's structure cospans, and Baez and Masters open Petri nets and open commutative monoidal categories. They state their theorems on operational semantics on open Petri nets in terms of the lax double functor from this double category of open Petri nets to open commutative monoidal categories. Also, David Jasmeyer's works with open dynamical systems, which he models through double categories. So it's, I think they're relevant right now because in that community, because people try to model complex systems through smaller systems by some sort of gluing process. And you want to be very precise on how you glue things, and you have to record things, what happens in the boundary once you glue. And also gluing is usually made through some sort of cospan, and cospans form a double category. So, well, they're very popular at the moment in ACT. So yeah. I want to focus on this very specific example of a double category. Well, sorry. In this slide here, in all examples here, every double category here has a better known horizontal bicategory. So the bicategory of morphisms is somehow better known as a double category of morphisms. There is, well, in the case of homotopy double group, it's probably not, but adjunctions maybe related, I don't know. Well, all these have bicategory versions, and you can think of all these constructions as having a bicategory and then extending this to a double category to express something. So we'll do that with algebras. So we'll first define a bicategory of algebras, which we write as mod. So write mod for the bicategory whose two cells are this form here. So again, you think of this as a globular square. So instead of having a globular diagram, you have a square where the vertical arrows are identities. So yeah, the two cells of this bicategory mod are like this. So objects are algebras, horizontal morphisms are bimodules over this algebras, and a two morphism in this diagram would be a bimodule morphism from this bimodule to this bimodule, or a morphism of abelian groups that sort of intertwines the actions of A and B in M and N. The horizontal identity is this function here, the function that associates to every algebra the algebra A as a bimodule over itself. And the horizontal composition is provided by a relative tensor product. So this forms a bicategory. The exchange identity in mod, which I didn't mention, but just says that if you stack if you have a system of 4 diagrams that you can compose vertically and then horizontally, then doing that is the same as composing horizontally and then composing vertically. This follows from the functoriality of the relative tensor product of bimodules. So this is this is a classic object, and it's also very smart. So it codifies Morida equivalence. So you can find isomorphisms in a bicategory, and two algebras are isomorphic in this bicategory if and only if they're Morida equivalent. And you can define adjoints in a bicategory. So a bimodule is adjoint if and only if it's finitely generated and projective. So this bicategory has a lot of information on the way we think of representations of algebras. Okay, so we can extend this to a double category. We write bracketed mod for the double category whose squares are of this form. So now vertices are again algebras, let's say A, B, C, and D. Horizontal morphisms are again bimodules. Now in this case, M is an AB bimodule, N is a CD bimodule. And now we have non-trivial vertical morphisms. In this case, F is a unital morphism from A to B, and G is a unital morphism from B to C. And now squares are a bit different. They're equivariant bimodule morphisms, which are morphisms of abelian groups satisfying this equation here. The horizontal identity and horizontal composition in bracketed mod are defined by the obvious functorial extensions of the horizontal identity, the function that associates to every algebra, it's bimodule, trivial bimodule, and the function that associates to every compatible pair of bimodules, so the relative tensor product. So there are obvious functorial extensions of this, and then this defines horizontal identity and horizontal composition. So the bicategory mod and the double category bracketed mod are related by this equation here. So the horizontal bicategory bracketed mod is this mod. So, well, that's fine and all, but why do we care about this? Well, we care about this because of the following. So in this bicategory mod, we have objects, horizontal morphisms, and two selves. We know how to take tensor products of algebras. We know how to take tensor products of bimodules, and we know how to take tensor products of bimodule morphisms. So this should be, and these three tensor products are symmetric, obviously. So this should make this bicategory mod into a symmetric monoidal bicategory. But the coherence data for the tensor product of algebras is defined in terms of algebra morphisms. But these algebra morphisms are not included in mod. The only morphisms that we have are bimodules. So well, we can encode morphisms of algebras as bimodules, and then we can try to make this into a symmetric monoidal bicategory. But symmetric monoidal bicategories are very, very difficult objects to define and to work with. These are some references on the definition of a symmetric monoidal bicategory, but it's a really long list of axioms that are a bit excessive for this case. We're in a very easy case where we know what the tensor product is. We have coherence data, which is morphisms of algebras, and it's very easily proven that this satisfies what should satisfy, but symmetric monoidal bicategories seem to be something else. So we need a different language to express this symmetric monoidal structure on bimodules. Well, the tensor product on vertices, edges, and squares on bracketed mod provide bracketed mod with the structure of a commutative pseudomonoid in double categories. So we have two categories, a category of objects. So this is the category of algebras and morphisms. And we have a category of squares whose objects are bimodules and morphisms are squares. And we could take tensor product on each of those two categories. This tensor product makes them into symmetric monoidal categories. And just checking some very easy compatibility conditions, we can make that into what is known as a symmetric monoidal double category. So just a monoid internal to the two category of double categories. So this is a much easier and natural object to define. But well, obviously the question is, so suppose, okay, so we define a symmetric monoidal structure on our double category bracketed mod, but I mean, we're interested in mod. Does that descend into a symmetric monoidal structure in mod? And the answer is yes, and yes because of frame bicategories, because bracketed mod is what is known as a frame bicategory. So I won't define what this means until the end of the talk, but yet this is where the frame bicategory thing goes in. So the fact that bracketed mod satisfies this condition makes it so that this easier structure that we can define on it, a symmetric monoidal structure, descends into a symmetric monoidal structure on this horizontal bicategory, which in principle would be a lot more difficult to define. So yeah, there's a whole preprint on this by Mike Schulman. Yeah, very nice work, very beautiful work. So in it, he argues that these double categories are actually the correct framework to equip, in this case, algebras with a two-dimensional symmetric monoidal structure. And he points out the following observation, so that there is essentially, or not essentially, there's two types of bicategory, exemplified by categories and by bimodules. So categories have categories as objects, functors as morphisms, horizontal morphisms or one-dimensional morphisms, and natural transformations as two morphisms. So the horizontal morphisms are a type of function, and composition is strictly associative. And this is sort of the correct way of comparing categories. While mod has objects, algebras, horizontal morphisms, bimodules, and two morphisms, bimodule morphisms. And the horizontal morphisms are not really morphisms. They're other types of objects parameterized by or original objects. The correct notion of morphism between algebras, well, it's morphisms of algebras, unitary morphisms. So this is not directly included in our bicategory, as I mentioned before, so we should just try to include it. So bicategories fitting this description are referred to as mod-like bicategories in this paper here, or I guess in the community. So these are bicategories whose subjects, or well, mod-like bicategories are categories that fit this bill here. Bicategories whose objects are some sort of algebra, whose horizontal morphisms are some sort of bimodule, and where two morphisms are bimodule morphisms are obviously mod-like. So if you have a mod-like bicategory, a category that looks like the category, a bicategory that looks like the bicategory of bimodules, then if it's called B, then B should have a category of function or correct morphisms of objects. We call this B star. So if we're in this situation, it should be expected that there should be a clear lift of our bicategory to a double category, having the correct notion of morphism as vertical morphism, and such that the horizontal bicategory is the bicategory that we started with. And if we have a natural symmetric monoidal structure in our bicategory that we can't prove, that is, that makes our bicategory into a symmetric monoidal bicategory, because the definition of a symmetric monoidal bicategory doesn't fit what we want. In this case, it is expected that we can lift our bicategory to a double category, then define a symmetric monoidal double category. And we should expect that this is a frame bicategory, which again, I haven't defined. And so the horizontalization of the symmetric monoidal structure on the double category descends to a symmetric monoidal structure on the underlying bicategory. So yeah, this is the idea. We should expect this. Well, I think I'll skip this slide, but yeah, there's an important example, as I mentioned in the beginning, where this, we don't know if this happens. This is binomial algebras, Hilbert bimodules, and bounded intertwiners. So this defines a bicategory, clearly mod-like. There's a correct notion of morphisms between binomial algebras, which are binomial algebra morphisms or normal morphisms, which are not included in our mod-like bicategory. So we should expect a lift to a double category of equivariant binomial algebra, equivariant morphisms of Hilbert bimodules over binomial algebras. We have a natural tensor product of binomial algebras, bimodules, and intertwiners. So we should be able to define asymmetric monoidal structure on this lift in such a way that this descends to asymmetric monoidal structure in our bicategory of binomial algebras. But again, there are no techniques in analysis that tell us how to define this double category of binomial algebras. So yeah, I'll just breeze through this. Oh, sorry. Here, Bartels, Douglas, and Henriques do define a double category of binomial algebras, but not of all binomial algebras, just a smaller class of binomial algebras where techniques in binomial algebras actually do work. These are called semi-simple, and vertical morphisms are finite Jones index morphisms. I called this BDH by Bartels, Douglas, and Henriques. So the details here are not that important. So you just have this bicategory, correct notion of morphisms, tensor product, or symmetric monoidal structure. We want to extend this to a double category, frame bicategory. We want to define a symmetric monoidal structure on this double category in such a way that this descends to a symmetric monoidal structure on our bicategory. This has been done for a smaller class for a smaller bicategory and a smaller class or a category of vertical or correct morphisms. So we would like to extend this to the general case. And there are no techniques in the theory of these things that tell us how to do this. So we should do this categorically or diagrammatically or in a way, I don't know, somehow. So the strategy that I propose is the following. So the theory, again, this theory of binomial algebras does not give us direct tools to extend this smaller double category. And well, there are some lifting techniques, especially in Schulman's paper, but he assumes a lot of very strong conditions. You have to assume that the symmetric monoidal structure on your bicategory is in part co-Cartesian, which is not the case. He has this general construction of bimodules over a symmetric monoidal category that doesn't work in this case because of the topology of binomial algebras. So long story short, no, there's no, from the analysis part, there is no way of doing this. And from the category theory part, there's no developed techniques to do this. So, well, let's just try to understand the structure that we want to define and know that it exists in terms of its, say, surrounding categorical structure. That would be the category of double categories of binomial algebras, not necessarily extensions of this thing. So pictorially, this is a drawing from David Spivak and Brandon Fong's book. So this is meant to represent a category. And so let's say we have a question mark here, which is the extension that we want to define. And so to know things about this, we just want to know how it interacts with the rest of this thing or with a neighborhood or something. If we get some information on the external behavior of this thing, then maybe we can just sort of get closer to knowing how to define it. Well, an obvious question is this drawing here non-empty in this case? So is there, okay, we're interested in a double category of binomial algebras extending this thing, but we don't even know if a double category of binomial algebras exists at all. So, well, that's the first question, of course. And well, I'm talking about binomial algebras, but that this is a general situation. So you have a bicategory and a category of correct morphisms. Is there a double category that sort of codifies this? Is there a double category of equivariant two cells equivariant with respect to your correct notion of morphism? So, okay, so this is the problem that I'm thinking about. So let's try to put names and things to say them quickly. So a decorated bicategory is a pair of B star comma B, where B star is a category and B is a bicategory, such that the objects of B star and B are the same. So represent decorated bicategories is a bunch of diagrams of this form. So in my definition, this should be globular diagrams and vertical morphisms. So we want to think of a decorated bicategory as a bicategory, let's say a mod-like bicategory, and the decoration is the correct notion of morphism, like the category of good morphisms that we want to include in our bicategory. An example of this is, of course, suppose C is a double category, then the pair formed by the category of objects of the double category and the horizontal bicategory. This is a decorated bicategory. So you write this as H star C. So this is a nod to the horizontalization, or this is a horizontalization with a little bit more. It's a horizontalization that just remembers the vertical arrows and just that. We call this decorated bicategory the decorated horizontalization of the double category C. Okay. So yeah, so we have the following problem. So given a decorated bicategory B star comma B, we want to find double category C such that the decorated horizontalization of C is our original decorated bicategory. We call any such double category C an internalization of B star comma B. So B star comma B is a bicategory, so it's defined through enrichment plus something else, decoration, and we want to define an internal category that sort of defines this structure. So we call this internalization. So I'm not sure if this is the best name, but that's what I call them. So can we understand the internalizations of a decorated bicategory? Or more elementarily, is the decorated horizontalization construction generic? That is, if I have a decorated bicategory, can I always interpret this as the decorated horizontalization of some double category? Can we extend any decorated bicategory to a double category? We think of the above problem as a problem of coherently filling hollow squares of this form. So if we're giving a decorated bicategory B star comma B, again, this is a collection of drawings like this. So we can take vertices. So all vertices are, the collection of all these vertices are the same. So we can take vertices, we can take vertical morphisms and horizontal morphisms, and we can form squares without a filler. And so the question is, can we fill these squares into a double category, fixing these vertical arrows and fixing the globular diagrams? So problems of this sort have been treated before, especially in strict homotopy theory by Brown and his collaborators, when proving the two-dimensional Seifert-van Kampen theorem. So I was meant to write a reference here. This is much older than 2011, but This is a book by Brown, Higgins, and Silvera where the actual proof in detail is there. And you can see there that he has, well, there's a notion of homotopy, well, relative to boundary, which is a globular thing, and arguments don't work in that case, so you have to extend to squares in a minimal way, fixing all the structure. So this has been treated. And of course, in frame by categories, which again, I haven't defined, but I'll just say that the definition of a frame by category is essentially this idea. You have some sort of frame, and then you can fill it, you want to fill it in some sort of canonical way. Okay, so this is decorated by categories and internalizations. So we want to find solutions to this, and it turns out we can find minimal solutions. If we have a solution, then we can restrict it to the smallest possible solution within that larger solution. So suppose C is a double category. Write gamma C for the minimal sub-double category C containing all the horizontal identities and all the globular squares of C. So this is gamma C. So gamma for globular. So we have this lemma. So if C is a double category, then the decorated horizontalization of C is equal to the decorated horizontalization of gamma C. So decorated horizontalization of a double category is the same as the decorated horizontalization of this smaller category. And moreover, if D is any sub-double category of C, satisfying this equation here, the same equation as over here, then gamma C is a sub-double category of D. So if we start with a double category C, we're interested in its decorated horizontalization, then this decorated horizontalization is the same as the decorated horizontalization of this gamma C. And this is the minimal sub-double category that satisfied this condition. Yeah, so C is a solution to the internalization problem for the decorated horizontalization of our double category C. Number one says that so is this smaller double category gamma C. And two, this says that gamma C is the minimal solution contained in C. We call gamma C the globularly generated piece of C. So it's a sub-double category generated by globular squares. So it's the minimal double category that contains all the squares. So we have the following question. Can we understand this sort of minimal solutions to the internalization problem outside the context of an ambient category C? Can we study them separately? And the answer is yes. So we say that a double category C is globularly generated if any of the following three equivalent conditions are satisfied. So C is equal to its globularly generated piece. C is generated as a double category by its globular squares, and or C contains no proper sub-double category D such that this equation here is satisfied. So every double category C is a solution to the internalization problem of its decorated horizontalization. Globularly generated categories are the minimal solutions. These are the double categories that such that there's no proper sub-double category that is also a solution. So yeah, these are very good. So pictorially, a double category is globularly generated if every square of C admits a subdivision like this. So this is a square that is subdivided as vertical composition and horizontal composition of smaller squares, where every smaller square is either a horizontal identity or a globular square. So these are the squares of globularly generated double categories. So these are very easy squares. Or in a way, well, I mean, the compositions might be very complicated, as we'll see, but the squares that are involved are the easiest possible squares. And all the information on the existence of internalization is contained on double categories whose squares are all of this form. So that's very good. So the equation gamma squared C equals gamma C is satisfied for every double category C. So if you have a double category C, you take its globularly generated double category, and then you take the globularly generated piece of that, then that's the globularly generated piece of the original double category. So the globularly generated piece of a double category is always globularly generated. And so the globularly generated piece, gamma C of a double category C is the maximal globularly generated sub-double category of the double category C. So globularly generated double categories are the minimal solutions to internalization problems. And every double category contains canonically a maximal globularly generated sub-double category, which is a solution to the same problem of internalization as the original double category. We can put this categorically very nicely or very neatly. So remember that we organize double categories into a two category. then we can take the sub. We have to say some things about double natural transformation, so I'll just stick with the one-dimensional stuff. So dcat now denotes the category of double categories, called gcat, the sub category of globularly generated double category, sorry. And write bcat star for the category of decorated bicategories and decorated pseudofunctors. I didn't define what a decorated pseudofunctor is, but it's what you might imagine. So it's just a pseudofunctor, a functor, and they are the same in objects. So the function associating to every double category, its globularly generated piece, extends to a functor from double categories to globularly generated double categories. This is a Grothendieck fibration. It's actually more, so it extends to a two functor, and it's actually a two core reflector. But well, we're not going to use this, so we're just going to say that this is a fibration. So double categories can be indexed by globularly generated double categories. So that's a very good thing. Remember that we're interested in internalization, and these are the minimal solutions. So we can just partition double categories into fibers where every fiber has a globularly generated base, or is parametrized by a globularly generated base. The functor associating to every double category, its decorated horizontalization extends to a functor now from double categories to decorated bicategories, and the following triangle commutes. So we have this decorated horizontalization functor, which is the one that we're interested in. We're trying to find if a decorated bicategory is here, then we're trying to study solutions to this double categories where this goes to here. But this double category is fibered through this category here. And this functor here restricts to a functor from here to here, making this triangle commute. So the H star functor here is constant along this fibers of our fibration. So the lesson here is that I'm just trying to say this in different ways, but the idea is if we're interested in internalizations, we better first study the basis of this fibration gamma. That is, we should study globularly generated double categories. I hope I convinced you of this. So this is just all this is just to convince you that globularly generated double categories are somewhat interesting. Well, so sometimes it seems like this double globularly generated condition is trivial. It seems it's almost trivial, but it's not. It's very delicate. So to prove this, I made this computation of the globularly generated piece of bracketed mod. So we know this double category. What is its globularly generated piece? Is this trivial or is it not trivial? Well, let's start with this lemma that tells us how do squares in a globularly generated double category look. So suppose C is a double category. Suppose phi is a square in C. And suppose phi is not globular, but it's globularly generated. That is, it's in the globularly generated piece of C. Then in that case, the horizontal source and target of phi are the same, or the left and right frame of phi are the same. There is every non-globular, globularly generated square in a double category is a horizontal endomorphism. If you start with a double category and you want to compute its globularly generated piece, well, we already know that the horizontal, the decorated horizontalization of the globularly generated piece is the same as the decorated horizontalization of the original bicategory. So we know it's objects, it's horizontal endomorphisms, it's horizontal morphisms, it's vertical morphisms, and it's globular squares. So we just need to say what are the non-globular, globularly generated squares. Again, now through this lemma, we know that these are horizontal endomorphisms. So, okay, we'll use this. So I made up this name, but I don't know. It's suppose R and S are algebras, and this is a horizontal endomorphism square from bimodule R bimodule M to an R and S bimodule N. Then we'll say that this is two subcyclic if there exist bimodules L and K of N, such that this here, as an R bimodule, restricting scalars on R by F, this is cyclic. This is cyclic as an S bimodule, and the image of your morphism here is contained in L. So this is a bit strange, but well, obviously, horizontal identities are two subcyclic. So if you have a horizontal identity here, then this is contained in the image of R under this F, which is cyclic as an R bimodule, and it's contained in S as an S bimodule, which is cyclic as an S by module. So horizontal identities are two subcyclic. An example of an equivariant morphism that is not two subcyclic is this here. So this is the inclusion of Z into Q, and this is the square here. So sorry, there should be a square here and a square here. So this is not two subcyclic because the image of this is not contained in a cyclic submodule of this because this has rank 2, of course. It's easy to cook up examples of non-horizontal identities, two subcyclic equivariant morphisms. So yeah, two subcyclic, I don't know, it's just not trivial. It's not every horizontal endomorphism. It's not just horizontal identities. So we have the following lemma. So the non-globular squares of gamma bracketed mod are two subcyclic squares. So this might or might not mean anything. The fact that, what this means is that the globularly generated piece of this double category that we know very well is not trivial. Something that is not just globular squares and horizontal identities, and it's not just all the horizontal squares of your double category. So there's some subtleties to this gamma construction. Okay, so we define globularly generated double categories. We parameterize double categories through globularly generated double categories. We said that these are the minimal solutions to the problem that we're interested in. And they seem like trivial double categories, but they're not. But they also seem like something that we should be able to understand somewhat. Yeah, we can understand them somewhat. So what we can say something about them. So globularly generated double categories are canonically filtered. They come with a filtration. How do we define this filtration? So we define it inductively. So first, suppose C is a globularly generated double category, write H0 for the set of all globular squares and horizontal identities, so the generators for each double category. Then write V1 for the category of vertical compositions of these things. So, okay, write V1. This is the first term of the filtration. Suppose we have defined V1, V2 to Bn minus 1. Now we need to define Bn. So we first start with an auxiliary set or pseudo category. We define Hn to be all the horizontal compositions of elements of squares in Vn minus 1. And then we make Vn to be the category of vertical compositions of squares in Hn. So this might be a bit obscure, but I'll try to explain this a little bit better soon. What we have is a sequence of categories, a chain of categories, such that the limit is the category of squares of C. So yeah, this is a filtration. We call this the vertical filtration of the globularly generated double category C. So every globularly generated double category comes with this vertical filtration. So this vertical filtration sort of organizes all the squares into these compositions into horizontal identities in globular squares. So to make this a little bit more clear, suppose C is a globularly generated double category. So I'm going to explain in a bit more detail what the vertical filtration does. So think of globular and horizontal identity squares of C as squares of, say, complexity 0. So the easiest possible squares. So we draw them as squares marked with a 0. So this is the squares that we start with, the easiest ones. H0 in our definition of the vertical filtration is the collection of this complexity 0 squares. Okay, now what do? We take all these complexity 0 squares and we just compose them vertically. We call this V1 in the previous definition. So geometrically, squares in V1 or squares of complexity less than or equal to 1 are squares that can be subdivided into a vertical composition of squares of complexity 0. So we denote these squares like this, just marking them with a 1. So these are squares that are not totally trivial, but that we can decompose into vertical composition of trivial squares, let's say. So these are, the complexity is just almost, we're including squares with 0 in here. So that's why we have the less than or equal. We can say these are squares of complexity 1. Okay, so suppose we're given two horizontally compatible squares of complexity less than or equal to 1 phi m psi. So these admit vertical subdivisions as squares of complexity 0. So it might be the case that when we compose them horizontally, we can organize this decompositions as vertical compositions of complexity zero squares in such a way that we can compose the complexity zero squares horizontally, and then we can compose vertically. So in that case, this horizontal composition obviously has complexity less than or equal to 1. But we can't always do this. So this doesn't happen in general. It can happen that we have two complexity less than or equal to 1 squares, phi and psi. We compose them horizontally, but it can be the case that whenever we take the composition of phi as a vertical composition of complexity zero squares, and we take another decomposition of psi, or a decomposition of psi as a vertical composition of complexity zero squares, then we can't match them together. And so we can't make them into a complexity less than or equal to 1 square. So we call this, we say that horizontal compositions like this are squares of complexity less than or equal to 1 plus 1/2. The 1/2 is just the fact that we can compose them horizontally. Then we compose these vertically. Sometimes these vertical compositions can be rearranged, sometimes not. When they can't be rearranged, we call these vertical compositions squares of complexity 2. So in general, suppose we have defined squares of complexity less than or equal to n minus 1, then squares of complexity less than or equal to n minus 1/2. Our squares can be subdivided as horizontal compositions of squares of complexity n minus 1/2. And then we take vertical compositions of these things, and then we define squares of complexity less than or equal to n. So these are the squares that can be subdivided as vertical compositions of squares like this, where each of this can be subdivided like this. So yeah, so we just start with our generators, horizontal identities and globular squares, and we compose them vertically. We compose them horizontally. Sometimes these compositions can be rearranged, sometimes they can't. Then we compose vertically. Sometimes we can rearrange, sometimes they can't. And so sometimes things become very complicated and we can't simplify. So the vertical filtration sort of organizes this. Yeah, so the VNs form the filtration. So the fact that the VNs form a filtration of a globularly generated double category C is that means that every square in a globularly generated double category has some measure of complexity. We can actually put this into invariants. Suppose C is a double category, a globularly generated double category. Suppose phi is a square in C. So we write L phi for the minimal n such that phi is an element square on the nth term of the vertical filtration. That is, L phi is the minimal n such that phi is of complexity less than or equal to n. So we call this L phi the vertical length, or the length of the square phi. We can extend this to define the length of a globularly generated double category. This is the maximal length of its squares. And so this is for a globularly generated double category. But again, globularly generated double categories are co-reflective in general double categories. So we can define the length of a general double category just by restricting to your globularly generated piece and then taking the length. So this defines invariance on double categories. I've talked about this with Bob Perret a few times, and he has expressed a very strong interest in a numerical invariance on double categories. And this does this, which is, yeah, very nice actually. Okay, so this length measures the complexity of mixed compositions of horizontal identity and globular squares on a double category C. So if a double category or a globularly generated double category L has length 1, then we can say a lot about its squares. We can say, of course, we know that the squares are globularly generated. They can subdivide into horizontal identities and globular squares. But if this is of length 1, then we can say this subdivision is like this. So it's very easy. So every square can be made into a vertical composition of horizontal identities and globular squares. Actually, the length of the trivial double category associated to a bicategory is 1. Quintets, again, is 1. Of bracketed mod is 1. Of the Bartels-Douglas-Henriquez double category is 1. So yeah, of course, the question is this trivial? Well, I just realized that maybe I'm going over time. How much time do I have, Mason? Just
well, You should be finishing up, but another 5 minutes for sure.
Okay, cool, great. So yeah, this is a bit long, I'm sorry. So, well, I'll skip this. So this is a way, I have a way of constructing.
1 second, you didn't answer your question about is it trivial? 1 second, that was a good question.
Oh, sorry, yeah. So we have this invariant, L, the length. And so as I said, if you have your globularly generated double category, which we already know they're not trivial, but this length tells you, so the complexity of the subdivisions of squares into globular and horizontal identity squares. If this is 1, then all squares can be written like this. This is very good. And all our examples that I have here are of length 1. So the question is, are there any double categories of length different than 1? And so well, there's this technique for constructing globularly generated double categories from decorated bicategories through a free functor on the decorated horizontalization. I call this the free globularly generated double category associated to a decorated bicategory. So the details are not important. This was the next slide. But essentially what you try to do is to reconstruct the vertical filtration formally from the data of your decorated bicategory. This is not an internalization in general, but it gives you a globularly generated double category. And through this construction, I could construct a globularly generated double category of length 2. And then that extended to globularly generated double categories of length n for every n and of length infinity. So this example looks sort of like this. So you start with your bicategory, 3 objects. These red arrows mean that these are horizontal identities. And you only have 1 non-trivial 2 morphism from here to here. And decorate this by this category here. So just you get 1 arrow here, 2 arrows here, and you suppose these 2 compositions are this purple arrow. And so you decorate this with this horizontal red things, this with this horizontal red things, and 1 non-trivial morphism, and this horizontal things here. And with this, you can form a complexity 2 square like this. So this might be a bit weird, but you just take this, the horizontal identity of this thing, the horizontal identity of this thing, and the horizontal identity of this thing, and you have the square, this non-trivial square, and you compose these 2 things vertically. This is horizontally compatible because the source is this thing here, the red arrow. And yeah, I could prove that the horizontal composition of this cannot be reorganized into a vertical composition of horizontal identities and globular squares. So this has complexity 2. And using the same ideas, I could define squares in more complicated double categories of complexity n for every n, and then of complexity arbitrarily large so that the length is infinite. So this length is not trivial. Yeah, that's a good thing. There's a way of bounding this length for any, so if you have a globularly generated double category, this free globularly generated double category construction that I briefly mentioned projects into this globularly generated double category with respect to the decorated horizontalization. So we can bound the length of any globularly generated double category in terms of the data of its decorated horizontalization. So, well, I'll just skip this. It's not important. It's not as important. Let's just say that I have ways of bounding length in terms of just the data of the decorated bicategory. So I can define the length of a bicategory with respect to a correct notion of morphisms, which was very good. That was very nice. And okay, so now we come to frame bicategories, so which were sort of the main thing in the title. So just very quickly, some of these things are important and some are not as important. Frame bicategory is a double category C such that any of the following 3 equivalent conditions are satisfied. So we have a left frame and right frame functor, or a horizontal source and target functor. We can take the product. So this product is a fibration, if and only if this is an up fibration. So this is a bifibration, or equivalently, for every vertical morphism in C, there exist horizontal morphisms that look like this, and squares that sort of look like this and satisfy certain equations. These are called the companion and conjoint of the vertical morphism F. This is not as important, but we want to think of this companion and conjoint as changes of bases. So essentially a frame bicategory is a double category where you can change bases. This is put in terms of vibrations and not vibrations. Bracketed mod is a frame bicategory. All the double categories that I mentioned before are frame bicategories. Morphisms, the homotopy, double groupoid, adjoints, decorated cospans, polynomial, comonoids, and Bartels, Douglas, and Henrik is double category of binomial algebras. And again, the important thing about frame bicategories is I had an explanation on why this was nice, but this theorem here. If C is a symmetric monoidal frame bicategory, there's the definition of this thing is very easy and relatively easy and quick. It's just the definition of two symmetric monoidal categories plus some coherence conditions. Then every choice of cleavage, so this again is a vibration. So if you choose Cartesian arrows, then the symmetric monoidal double category, the symmetric monoidal structure on this frame bicategory defines a symmetric monoidal structure on its horizontal bicategory. So we do want to, with this globularly generated double category theory, we know how we can say things about if you have a mod-like bicategory with a correct notion of morphisms, we can say things about double categories of equivariant morphisms in general. So this is sort of like the bare minimum conditions that you get, that you want from a double category like this, but it allows you to say things about these things. But okay, that's a good thing, but we were interested in symmetric monoidal structures. So we want to lift, not just in general, but we want to lift to frame bicategories. The obvious question would be, when is a globularly generated double category a frame bicategory? And the answer is, yeah, not very good. Globularly generated frame bicategories are vertically trivial. The only case in which a globularly generated double category is a frame bicategory is when the vertical arrows are identities. These are symmetric monoidal categories. Monoidal categories. Why is this? Well, I breezed through this, but the definition of a frame bicategory requires these squares here. But remember that in a globularly generated double category, every non-globular square is a horizontal identity. So yeah, this should be trivial. But I mean, that's not that bad. I mean, so we had double categories indexed by globularly generated double categories. So, well, this says that in general, we can't expect for bases of this vibration to be framed by categories. But I mean, they obviously always represent some frame by category when they do. I mean, every frame by category has a globularly generated base. So the question is, can we say anything about globularly generated double categories that are the globularly generated piece of a frame by category? Can we say anything about the basis on this vibration gamma of frame by categories? And finally, well, what is the length of a frame by category? This length function just sort of tells you how difficult the globularly generated piece of a double category is. And so we're interested in frame by categories. We can define the length of a frame by category by its globularly generated piece. How complex are these double categories, the globularly generated pieces of frame by categories? My conjecture is that this is one, and this is based on all these computations here. These are all frame by categories. They all have length 1. And I didn't have time to mention this, but frame by categories are sort of, the definition is sort of once you unwind it, it sort of looks a lot like the globularly generated double category condition, almost with a twist, with lots of things in between, but there's something that looks like it, and especially, well, not the globularly generated double category condition, globularly generated double category condition of length 1. So there is some evidence that this should be the case. If this is the case, just recall that we're starting with a mod-like bicategory, or a bicategory in general, with a correct notion of vertical morphisms. We want to end a symmetric monoidal structure, or a moral symmetric monoidal structure on our bicategory. And we want to extend all this to a frame bicategory on which we can define a correct notion of symmetric monoidal structure in such a way that it descends to what we want, a symmetric monoidal structure on our original bicategory. This conjecture would say that if you don't know what this double category is, well, you just have to look at squares of length 1. You just have to compose horizontal identities and globular squares, which you already know, and see when that defines a frame bicategory. So this is not just based on this sort of question, I don't know, philosophical or a curious question of defining invariants on double categories and having the special case of frame bicategories. This would be extremely useful for defining symmetric monoidal structures. Yeah, so the references for this work are these. If anyone's inclined to read this last paper, there's a couple of mistakes which I'm meant to correct soon. So, but yeah, these are the references. So yeah, thank you very much.
Thank you very much. 1 second. Ross Street logged off, but before he logged off, he asked a question.
Yes, sure, please.
Okay, so what is the length of a, I'm sure he'll listen to it on the video. What is the length of the double category of squares in the bicategory of profunctors where the verticals are functors?
1.
1, I guess, yeah, but I must go now. So he was right. He said 1. Yeah,
it's 1. It's that's exactly the yeah. Of course, Ross says, but yeah, that's the right intuition. This is a frame. This is sort of like the 3rd or 4th example of a frame bicategory, and yeah, the length is, once you do the computations, it's exactly 1. So the thing is that these profunctors have base change, but in a very specific way, as algebras and polynomial algebras, and it's not exactly what Schulman, or it's not phrased in the exact same way as the definition of a frame bicategory. But if you use it in any of these specific cases, then you can actually prove that length is 1. So essentially, the thing is that in profunctors and in all of these double categories that I computed the length of, you can you have a good interaction between horizontal squares and globular squares. So you can move them around in a good way, in such a way that if you compose 2 complexity 1 squares horizontally, then you can move things around canonically and then things match. So yeah, you can do that in profunctors. So that was a very good question, and the answer is yes, this one.
Okay. Any other, Ray, did you have a question?
I have one. I was just thanking the speaker.
Oh, okay.
Thank you very much.
Okay. Okay, thank you. Anybody else? Any other questions? Okay, so let's thank our speaker again. Thank you very much. I just want to say, first of all, this is the last talk of the semester. Ray, you're gotten feedback. Okay, this is the last talk of the semester. It was a great semester. We had some great talks. This is an excellent talk. We'll start again in September, I guess. And if anybody wants to speak or knows somebody that wants to speak, please send them my way. And thank you very much, Juan. When you make progress, you got to come back and tell us more about it. Okay.
Sure, I'd love to.
Okay.
Thank you so much.
Thank you very much, everybody. Take care. Good night, and thanks for a great semester.
Thank you.
Take care.